I welcome you again for this NPTEL lecture on earthquake resistant design of foundations. And under this course, as we discussed earlier, we have 5 modules and we are right now working on pile foundations. And during the pile foundations, we have already 2 lectures on the pile foundations, and what we have covered is piles for vertical loads and when it is subjected to static loads only. So, we have not considered. Today what we are going to consider is perhaps the most important part of this course on earthquake resistant design of foundations. As I mentioned earlier, that pile foundations are the important to be used during the earthquakes or lateral loads. So, the design of piles when they are subjected to lateral loads we are going to consider, and today we are going to talk about that. So, when we talk about lateral loads on piles, these are the issues which we are going to talk. First thing is we are going to talk about introduction, then we are going to talk conventional methods of analysis, then elastic methods using Winkler approach. Later we are going to talk about solution for piles in cohesive soils, solution for piles in clay, and then design procedures and numerical examples. So, when we talk about, let us talk introduction on lateral load on piles. You may be aware that pile foundations are subjected to lateral load and moments which comes due to wind loads or seismic forces in buildings, earth pressure in retaining walls and abutments. It could be due to water pressure in the waterfront structures or offshore structures, which is also subjected to lateral load. So, what we are going to talk is not will be applicable during the earthquake, but it will be equally applicable for any type of lateral load, whether it is due to wind, whether it is due to water pressure, or it may be due to earth pressure on retaining walls. The conventional analysis, which assumes that piles do not resist any load in the bending and the soil reactions to piles due to lateral movement, is negligible. So, this is the in the conventional approach. That means, the flexural rigidity of the piles is not considered, as well as the piles will not be able to carry the lateral load. This is a conventional approach. However, according to this approach, conventional approach, the vertical piles cannot resist lateral loads, and as a result you require inclined piles or what is called battered piles are necessary to resist the lateral loads. But this approach is unrealistic. And why it is unrealistic, let me explain to you. Actually, you know that this is similar to what you can consider like a column. When you talk about a column is free, it is not supported by the soil, it may be only, but pile is not free, it is supported. Even if you have vertical pile, still in fact it will be able to carry some lateral load. It is not necessary to carry the lateral load that you require the inclined pile, because simply the pile is supported by the soil, and whatever the soil capacity is there between when you apply some lateral load on the pile, soil will provide the support. So, that support is considered in the latter theories, while in conventional theories this is neglected. And so, latter theories account the bending of piles as well as that lateral support of the soil. So, when we talk about the latter theories, these available approaches can be grouped into 2 categories. One is based on elastic theories, another is based on plastic theories. So, we are going to talk in detail those approach based on elastic theories. Plastic theories will be little difficult to cover, because that will be based on finite element analysis and plasticity models. So, let us talk about conventional approach and then. So, continue with this. When we talk about elastic theories, which is most famous theories for lateral loads, is called by Reach and Matlock, proposed in 1956, which assumed the soil to be replaced by a series of closely spaced independent elastic springs, which is called Winkler's assumptions. The equation for a beam on elastic foundations utilizing the concept of subgrade modulus has been solved for different conditions, and after solution non-dimensional solutions have been given for a laterally loaded vertical piles to determine the variation of deflection, bending moment, shear force, soil reactions, etc. along the entire pile length. And while calculating this require a knowledge of elastic constants of the soil, which is Young's modulus E and Poisson's ratio. So, for calculation of deflections, bending moment and shear force, naturally we require two basic soil properties. One is Young's modulus or maybe shear modulus and the Poisson's ratio. So, once you know the Young's modulus and shear modulus, shear Poisson's ratio, then you can get the shear modulus. So, that is important. So, this was the introductory part on the piles on lateral loads. Now, let us talk about conventional method. When we talk about conventional method, the conventional methods are we are going to discuss it into two parts. First one is when piles are subjected to moments only and piles are subjected to lateral load Q. So, in this case I will like to explain that the pile which is subjected to moment is basically equivalent to a eccentric vertical loads. So, this is, if you recall, we have already discussed. So, this is in case of shallow foundation we have discussed, but for pile the same thing will be applicable. So, let us say this is pile, though this is diamond, and if I apply a central vertical load here V and a moment M. Now, this can be replaced by I can have this equivalent moment. So, you will have this can be simply replaced by central line, this one. So, a vertical load acting at an eccentricity E. So, this will create a moment basically. If I like do this apply, and then this will create a moment acting like this. So, in this case the moment should act in this direction, and so what you will have E will be simply M by V. So, this is equivalent. So, whether we say pile subjected to moment or what we call eccentric vertical loads. So, load is not centric. So, that is the same case. This thing we have discussed in detail when we talk about shallow foundations. So, and then the second is pile subjected to lateral load. So, let us discuss that when the piles are subjected to moment first. So, what are the assumptions? First assumption is that pile cap is assumed as rigid. Pile cap, what is we already discussed. The load on each pile due to moment is proportional to its distance from the center of gravity of the pile group. The settlement of pile is proportional to the load acting on this pile. So, for example, let us this is we have a pile group, 4 piles are there in a row. This is the center of gravity of pile group here, and then what you have at that in this case you have the loads are acting here downwards. So, what you have is this is subjected to a vertical load as well as moment. So, here the figure shows a pile group subjected to vertical load and the center of gravity of the group and a moment. Reaction in each pile is caused by a vertical load as well as moment, as is shown in the figure 1b and 1c. So, this is due to this the first figure shows the reaction cause. This is the plan, basically this is the plan which is obvious to you, and this is elevation of the, and then you have this shows the load in each pile due to vertical load, and this figure shows the load in each pile due to moment M. Now, what will happen? The total load coming on each pile will be the combination of this diagram and this diagram, which is shown here. So, you will get maximum on this side and minimum this side, and this is due to, you can say that eccentricity. If you recall that whatever we have discussed in the shallow foundation similarly. So, because this moment is acting this direction, that means this will be equivalent to a load acting at eccentricity. This will be the similar to acting at. So, in this case this will be equivalent to a load, vertical load, and this can be replaced simply by this, a vertical load, or I can say that sigma V is acting at an eccentricity E, where E is summation of E is given by this relation summation M or summation of V. So, because one of the assumption is here, one of the assumptions we have assumed is that from static equilibrium summation of moment should be 0, and summation of moment about what? Summation of moment about the center point CG of pile group about this point should be 0. So, here you take, let us say finally we get this bending moment P1, P2, P3, P1, P2, P3, P4 are the loads on each pile due to this moment M, and these will be proportional to the distance of the point from the CG. That means, where at the center of gravity there will be no p due to the moment. So, this will be 0 here, and as you go away its value increases. So, total will be if we take the moment about this CG. So, what will happen? So, this CG will be that P1 into D1 plus P2 into D2 plus P3 into D3 plus P4 D4. So, you have this second equation gives you the total moment, and then these are the linearly distributed, that means P1 and P2, P3, P4 are in proportion to their distances. So, equation 3a will be holding for the linear distribution of the loads, and then what we can have from equation 3a can be written in another form, that P2, P3, P4 can be found in terms of P1, and then finally we put all these numbers in equations 2 and we get equation 4a, which is summation of m in terms of P1. So, solving this 4a we can get the value of P1 in terms of m. So, you get summation of m d1 and summation of m d square. So, here d square is the distance square. If this was the case for first pile, so when you keep 2, 3, 4, so this generalized form of this equation can be written as Pn equal to summation of m. This is for one direction. Suppose if this where n is stands for the number of piles, if the moment summation of m is acting in another plane also, in that case you may have the similar equation as shown in 4d, and finally due to the moment as well as due to the vertical load, the total pressure coming on any pile can be find out from this relation, where you have this P equal to summation of V by n plus summation of d square dn plus dm. So, where n and m is your number for which you want to find this. So, this load. Okay. Let us have one numerical example and it will clarify that how this can be processed. Here you have a pile group of 8 piles. In a row you have 4 piles and you have 2 rows of the 4 piles each. The spacing between piles on x direction is 1 meter, while in the y direction is also along the y axis is also 1 meter. Now, this pile, this is in the elevation, in this direction this vertical load applied is 500 ton and a moment is applied which is about you have this one. So, this is about this moment will be acting about y axis. So, about y axis 500 ton per meter and about x axis it is 250 ton per meter, it is shown here. So, now these two moments are acting and the vertical load is acting. So, the pile is subjected to one vertical load and 2 moments. We need to find the load coming on each pile 1 to 8, and so that can be solved like this. For n equal to 8, summation of dn square will be like that this here. How this is calculated? You have for this here, if I talk that being the symmetrical about this axis, if I take the distances, n is measured from this side. So, you have 0.5 for these 2 piles and then you have 1.5 and the same thing is here, and the 2 rows you have. So, this can be calculated 2 times of 0.5 square plus 1, so 10 meter square. Same thing is when I have here along this axis there are 8 piles and each one have the distance 0.5 meter from this axis. So, it is 2 meter square, and then you put the numbers, all the numbers, 500 by 8 and 500 into 1.5 is the 4. The maximum load will be subject to pile number 1 will be subjected to maximum load and pile number 8 will be subjected to minimum load. How this comes? Actually, if in this equation, if I use plus here and plus here, then that will give you the maximum load. If I use minus in both places, then you naturally will get the minimum value. So, using the plus sign here. So, you have plus sign both the cases, then you get 200 ton. If I use the minus sign, then you get minus 750. Negative sign shows that is basically this is uplift. So, the pile 1 will be subjected, it will be here, sorry, this will be pile 8. So, this will be pile 8, P8 will be there. So, you have this minus 75 ton. So, you get here for uplift. Then continue with this. What you have the piles subjected to lateral loads, and earlier what we have considered the piles which was subjected to the moment only. Now, we are going to consider the piles which are subjected to lateral load, and in this case a vertical load is applied and a horizontal thrust is applied. Okay. So, a vertical load and horizontal thrust, if I combine both these loads, then you will get an inclined loading, and inclined load use is shown in this figure as R, okay. And R is shown here. How we can do this one? This can be done what is using this graphical method, and the solution can be found out using the graphical method, and that is called Culmann's graphical method. Culmann's graphical method is used. So, using this let us say this is the problem given here, and piles are grouped. So, what is done here? Piles are grouped according to their slope, that the piles in each group is subjected to equal axial loads. And the steps which require, first of all, draw a dimensional sketch of the pile foundation, locate the center line of each group of parallel piles. So, what is done here? You have let us say 1, 2 and 3 section. So, 1 may represent a pile group itself, where the center of each pile group is passing through this dotted line, for 2 inclined and 3 for vertical. So, now you have in this case let us say 3 pile groups or 3 piles where the center lines are known to us. So, locate the center line of each pile group of parallel piles. The next step, draw the resultant R of all action applied on the pile foundation. R intersect the center line of the piles in group 3 at point A. So, what is done? This is the R. So, the value of R is given to you, as well as this location where it is acting at the on the pile cap is also known. So, R is completely known. So, what we do? We extend the vector of R, and wherever it is cutting is called point A. So, this is the point A here, okay. And another thing what we do, so point A will be the point of direction of R wherever it intersect the center line of pile 3, okay. Then pile 1 and 2 we extend the center line of each and they intersect at point B. So, simply extend here. So, now you have A and B, and then we combined direction A B. So, what we do now, we resolve the force R into Q and V, where V is the vertical and Q will be have the same parallel to AB, okay. So, now this R load is divided in 2 parts. V will be carried by pile group 3, while Q will be carried by the combined pile group 1 and 2. Then you resolve again into Q into 2 components, one is Q1 and another is Q2, where Q1 you have this is acting here and Q2 is acting downward. So, what you have Q2 and Q1. So, Q1 is vertical and Q2 is parallel to this direction of center line of 2. So, Q1 load will be for group 1 and Q2 will be for group 2. So, this is how this resolving the different components are, we could find what the load sharing mechanism will be by pile group 1, 2 and 3. If you have more than 3 pile groups, then similar approach can be done. So, what we do? We have 1 pile group and then 3 are combined and then eliminating like this. So, this is more than 3 directions, the pile reactions are compounded further. The analysis described this ignore the capacity of soil to withstand the horizontal loads and the capacity of piles to withstand bending, hence these are not realistic analysis. So, in the conventional method there is a major drawback. So, basically the conventional method will be very uneconomical, it is conservative method. It assumes that soil is not providing any support to the pile and the pile do not have the bending capacity. So, both of these are unrealistic assumptions, because soil provides a support to pile, and the second thing is this pile being mostly of concrete, they have good bending capacity or flexural rigidity. So, due to this limitations, these conventional methods are now getting obsolete for pile design, but still for the simple cases these can be used to work out the pile load capacity, or at least to check the results from that. So, anything which is designed from other methods, like that can be checked that approximately that how it perform using conventional method. So, now we come ahead from the conventional method, then other methods, elastic methods, and then one part before elastic method is limit analysis. And in the limit analysis what is done? It is assumed that the maximum soil resistance acts against the pile as shown in the figure. So, you could see here P1 is the lateral load applied on the top of the pile. So, what will happen? So, the soil will try to provide resistance. So, this resistance which is provided by the soil was neglected by the conventional method. In fact, in the modeling for soil pile, the soil is replaced by spring and dashpot, and spring particularly if you do not consider the damping. So, but in the conventional method the soil is neglected. Here reaction which is when I apply some lateral load in this direction, so soil will try to resist it, and this resistance may be this side, and then there could be like that on another side depending on this. So, when the now here is the case, the second case, when the pile is subjected to vertical load, lateral load as well as moment. So, you could see it is subjected to P, M, Q, all three forces, which is the very general case, and what will happen, they will try to deflect the pile as well as bend. So, pile will undergo bending as well as deflection. So, you have this the reactions, soil reactions at each point will be simply P into Kx or Yx. What is Yx? Yx is the deformation at that particular depth x, where x is at different locations. So, I think this is something here in this axis there is something wrong. This is x axis and this is considered y here, it is other way, because y is the deflection in this direction and x is the depth. So, along the depth. So, this is here, and when you apply this load, so then you can have this deflected shape of the pile. So, this was for the limit analysis, but for the limit analysis that it is considering the limiting values of the soil, then more realistic analysis is called elastic method using Winkler approach, and this elastic method using Winkler approach we are going to discuss in detail. A laterally loaded pile often treated as a beam on an elastic foundation. Okay. So, this is the case, and according to Winkler, the elastic soil medium is replaced by a series of infinitely close independently elastic springs. So, this will be an elastic springs, not one, a number of springs will be there. So, the stiffness of these springs may be written as this will be again springs may be written as K equal to P by Y. So, what you have here, this is the, you could see this is a pile, actually pile is vertical, right. So, for understanding what we did, we have that so you can understand like this. In this case, this was your pile and soil provide the support from both sides, but time being assume that the soil support coming from the soil is all around the pile and the whole support is represented on one side. So, we have one side soil and one side pile. The one side soil support which you are considering is representing whole support all around the pile. Then now, if this is vertical, if I do that, I made this horizontal, soil is this side and then I put like this. So, what will happen? Now, your pile become a kind of a beam which is supported by soil, which is shown here. So, this is beam of, and the rigidity of the beam is EI, where EI is the flexural rigidity which is the same of the. So, instead actually the difference, this is let us say pile, if I do like this, this is can be considered like a beam which is supported on the soil springs. So, which is shown in this figure. So, what we can do here, what will happen when you apply the load from the top. So, W, what is W? W is like a lateral load. If it is a lateral load is acting like this, now I can consider like this. So, W is acting downward and this will try to deflect the pile, and when it is try to deflect the piles, you will get the that because it is concentrated load at the center. So, maximum deflection is expected at the center and it will get decrease, and soil will try to push it, soil will provide some support reaction. Now, this soil reaction, the value of this soil reaction depend on the deflection, and in this case it is expected that deflection is more at the center, less at the edges. So, the spring constant or spring value which is going to come at the center is expected to be more than the at the edges, because it will be. So, basically this stiffness of these springs is written as K equal to P or y, P into P divided by Y. So, the soil reactions, what will be the soil reaction? Soil reaction is load per unit length, that is in kilonewton per meter. So, what is expected for the, if you have keep the same deflection and the soil properties are also same, then P will be also throughout same, but if deflection is not being expected to be same. So, P is going to be more at the center for the same soil property. If I assume that all the springs have the same value of K. So, naturally Y is increasing at the center. So, you will get the more value of soil reaction at the center as the aces. So, depending on that. So anyway, so what is this here? The stiffness of the spring may be written by this way, and this stiffness is basically soil reaction divided by the deflection, and soil reaction is in kilonewton per meter, and if I divide this with the deflection, then you will get the value of K in kilonewton per. So, stiffness of soil is termed as the modulus of horizontal subgrade reaction, and the unit for K is in kilonewton per meter square. And the values of K, now the K which is said to be spring constant, it is not constant even if you have, let us say, because this is not the horizontal case, actually pile is like this. So, again we consider like this. So, what is expected that if you go down and down here, and the deflection may normally, if your soil get harder and denser, then the deflection may reduce at the down. So, depending on the where you are applying the load, and so what happens here, the values of K varies with the depth. That means, the values of spring constant is not constant with the depth, rather for the sandy soil it is expected that the values of this spring constant are increasing with the depth, but normally the variation is not so much in the case of clay or cohesive soils. So, let us first talk about kind of variation. So, this equation here shows the values of K varies with the depth, and you could see Kx equal to Kh into x Ls over n, where what is n? N is your some coefficient, and the value of n is more or less nearby 1. It could be 1, it could be little less than, it may be less than 1, or it could be greater than 1. So, even some cases n may be 0. So, it may be 0 to 1, and then when you go on the higher side it could be 1.5 or so, but not more than 2 should not be considered. So, basically the range of n may be between 0 to 2, but most of the cases it will be around 1. So, maybe more than 1 or less than 1 or less. So, and it depends on the value of n will depends on the type of soil. So, what is here? Kh, Kh is value of K at pile tip at x equal to Ls. So, what you can have? So, this equation can be basically represented if I consider n equal to 1. So, okay, in the next it is shown here. So, what you have for different cases here, it is shown here. So, Tarjagi, what Tarjagi have recommended? Tarjagi have recommended n equal to 1 for sand and n equal to 0 for clays. So, you could see that this is for the sand, this variation is linear. For the sand, variation of Kh is linear, while for clay it is constant. Okay. So, you have this one for the sand, if I assume n equal to 1, then I end up in this equation Kh into x by Ls. So, if I divide Kh by Ls, then I get another coefficient which is called constant or coefficient of modulus of subgrade reaction, and its unit is in kilonewton per meter cube. So, NH, and this is mostly applicable for sand. For clay, n may be 0, and once you assume n equal to 0, then Kx may be equal to Kh. That means, the value of this Kx is the same as the from top to bottom linear. So, this is the case here, and this these three figures are showing good variation for this value of K. So, now this coefficient of modulus of subgrade reaction eta h, it is very important, and we are going to use for in further analysis this coefficient. And before that, let us work on that. What is this how this what is called characteristic length of the pile. So, there is a one term called characteristic length of the pile, and which is defined using what is called L alpha, and what is that? We try to understand this one. What is the theory behind this? The Prakash and Saran in 1967 that reported test data on model piles subjected to horizontal load at 5 centimeter above the sand surface. The pile lengths are here. What the pile lengths they have considered for the testing: 10 centimeter, 20 centimeter, 30, 40, 50 and 60 centimeter. The deflection of the piles at the ground level are shown in this figure. It is seen that as the pile length increases, the ground deflection of a pile of constant cross section decreases at the same load, and the length L alpha is defined as the infinite length of the pile, and this would obviously be a function of the pile stiffness EI and soil stiffness K. So, what is happens here? You could see this in this figure 10, 20, 30, 40, 50, 60. Okay. Now, what is happening that if I see there is a gap between 10, 20, 20, 30, 40, but the 50 and 60 curves are very close. That means, for a given load, for example, if I assume for the load 8 kilogram force, then if I draw a line. So, you could see that when the deflections are decreasing when I go from 20 to, it is decreased very much when I go to 20, 30, but then rate of deflection decrease becomes very less here, and at the end there is hardly any difference. So, that means there will be length of the pile, after which there is not much difference on the deflection, and if you are no change in the deflection, even if you are going to increase the pile length, and that length will be defined as the infinite length of the pile, and this length will depends on stiffness EI and soil stiffness K. So, that means it will not only depends on the properties of the pile, but it will be depending on the soil properties also, and this is represented later on using a relative stiffness factor, which we are going to talk later. When we talk about vertical pile under the lateral load, then this stress, strain and load deformation relationships are invariably nonlinear as shown in this figure. For loads of less than 1/3 to 1/2 their ultimate values, the load deflection curve can be adequately expressed by a tangent modulus as shown here. So, that means what is you could see here, actual case is this is, but for the initial part up to this point it is almost linear. So, we can have load deflection relationship up to this point, that means the slope of this line curve is a constant and which can be represented by tangent modulus. However, after that this is not constant and the slope is varying at different values of deflection and other things. So, you need to find the value of modulus at different location and secant modulus, which is simply, so what you have in this case secant modulus, just joining this point and this point you get the secant modulus, and once you have this that this will keep varying. So, it is difficult that when you work with the secant modulus, so then every time it will keep changing. So, therefore, application of the linear elasticity solution is not justified, and we need to account for the nonlinearity for the load and pile deflections, and for this either we may employ repeated of the elastic theory and or the relationship between the secant modulus, and the modulus can be defined in terms of strain level. So, these things we are going to discuss later in the next part of the presentation. So, like this will be up to this point, and I will talk about this how to apply whatever we have discussed in this lecture for particularly modulus of subgrade reaction, and that need to be applied for when you have piles are subjected to the lateral loads. So, what let us what we have covered. So, I summarize it before I end today's lecture. Here is the topics which we have talked today, these are given here. So, what we have already talked about: introduction, conventional method of analysis, elastic method using Winkler approach, and then we have this talk about. So, these things are over. Up to this point we have finished, and in the next lecture we are going to talk on the topics solution for piles in cohesionless soils and piles in clay, and then some design procedure and numerical example. Thank you very much for your kind attention. Thanks.